Bismillah ar-Rahman ar-Rahim. In this chapter, the concept of production possibility set will be introduced. The positive dataset assumption is relaxed, and instead of assuming the data are positive, it is assumed that the data are semi-positive. Semi-positive means for each DMU we have all the inputs and outputs non-negative, but at least one input is positive and at least one output also is positive, means strict positive for each DMU. This will allow us to deal with applications which involve zero data in inputs and or outputs. The production possibility set composed of these inputs and outputs data as X and Y will also be introduced based on the production possibility set. We name it also PPS. The CCR model will be obtained in another way that it is shown. It is the dual problem of the CCR model which we had in the previous chapters. But what is the production possibility set? Production possibility set indeed contains all pair of inputs and outputs that the inputs can produce the outputs. So if we assume as before that the inputs of and outputs of DMU G is xj and yj, j from 1 to n for n DMUs, the production possibility set contains these DMUs plus some other pairs that also they are not exist, but it can be assumed that the input, the pair of inputs and outputs can be exist indeed. But semi-positive means for the inputs we have xj greater than or equal to 0, all its components, but xj is not 0, which means that it has at least one positive component. And the same for the outputs for all the DMUs. A pair of such semi-positive input X in Rm and Y output Y in Rs, because we assume that we have M inputs and S outputs for each DMU. This pair is called an activity and express them by the notation pair of X and Y. So the component of each such vector pair can be regarded as a semi-positive orthant point in n plus s dimensional linear vector space in which the subscript M and S specify the number of dimensions required to express inputs and outputs respectively. The set of feasible activities is called the production possibility set and is denoted here by P. For P, we postulate the following properties of P, the production possibility set. The first one, the observed activities means xj and yj for all j from 1 to n belongs to P. So the production possibility set contains all the observed DMUs or activities. The second postulate is if any activity belongs to P, then the activity which inputs and outputs are multiplied by a positive scalar T also belongs to P. We call this property the constant returns to a scale assumption. It means the outputs are increased or decreased with the same ratio that the inputs are increased or decreased. The third assumption or properties is that for any activity X and Y in P, any semi-positive activity X bar and Y bar, which X bar is bigger or equal to X and Y bar is less than or equal to Y, is included in P. This means any activity with input no less than X in any component and with output no greater than Y in any component is feasible. And we have also this postulate which says any semi-positive linear combination of activities in P belongs to P. Of course, we need another postulate that is not here, and we should add it, that says this P is the smallest set that satisfies to these postulates. So we should add another postulate which says P is the smallest set that satisfies these conditions. Arranging the data sets in matrix X and Y, we can define the production possibility set P satisfying these conditions by P, that is, as you see in 3.1. Of course, this is the smallest set that satisfies these conditions, these postulates. In this figure, you can see the production possibility set. For example, for these DMUs, when we have one input and one output, the line from origin through B is named efficient frontier. This set that contains all the DMUs and is a continuous set is named production possibility set. And now consider one of the DMUs, for example, DMU O. Here O can be 1, 2, or 2, n, because we have n decision-making units or DMUs. Each DMU have its input and output vector. So for DMU O, the inputs are in the vector x o, and y o is its output vector. So as you said before, for each DMU we want to know, this is of course input oriented model. We want to know if we could produce YO with smallest inputs. So we search in the production possibility set to find a pair of inputs and outputs that minimize the inputs, indeed, as you see here. When you minimize theta, when theta xo and yo yo belongs to p, you want to know if you can produce yo with the smallest input ratios. Now if we with the definition of P, we had production possibility set is all x and y's that satisfies the conditions you see before. That is, in matrix form, x multiplied by lambda is less than or equal to x, y multiplied by lambda is bigger than or equal to y, and lambda as a vector, as an n vector, is bigger than or equal to 0, means all of components are positive, indeed non-negative. So if we put P in this model, we would have minimize theta subject to x lambda is less than or equal to the inputs theta xo, and y lambda is bigger than or equal to the outputs of the DMU under the DMU which want to find its efficiency. That means DMU O. Here we have lambda is bigger than or equal to 0. By solving this model, we can see if less ratio of the inputs can produce the same at less at least the same outputs that DMU-O produces. Now we show this is the dual of the CCR model, which we explained in the previous section. For this purpose, we rewrite this model as minimize theta when theta xo minus x lambda is bigger than or equal to 0, is that lambda is non-negative, but theta is unrestricted in sign. So to write the dual, as you know from the linear programming, you give a vector of variables. Indeed, here we have m constraints. So this you have m component, and this have m components. I change the name to v. It is more standard. And for this, we use a vector of s components, because here we have s constraints. So this is a s variable, s vector. That means it has a s component. The dual would be maximizing v multiplied by 0, u multiplied by y, o. Here we assume v and u are row vectors. So the dual is maximize u, y, o subject to the constraint corresponding to theta will be vxo equal. It is equality because theta is unrestricted in sign. So it is vxo equal to 1. And the constraints corresponding to the lambda is uy minus vx. The right hand side, because we don't have lambda here, is 0, and since lambda is bigger than or equal to 0, so this constraint is in canonical form of the model that you know for maximization is bigger than, less than or equal to constraint. So we have these constraints here. Indeed, we have n constraints. This is one constraint, and since all the constraints are in the canonical form of minimization, so these variables are non-negative. So we have this. This is the CCR model we named LPO in the previous chapter. This model also is named multiplayer form of the CCR model, and this model that is named, and it is the dual of the LPO, is named the CCR model in envelope form. By changing the inequality to the equality form, we can also write the envelope model as minimize theta subject to the summation of indeed we write x lambda as this summation of lambda j x j. It was less than or equal to theta x, also this plus s like variables, as we name it, s minus, should be equal to theta x o. Here j is from 1 to n, and for the outputs we have this. Here all the lambda are non-negative, and s minus and s plus also are non-negative. So we have written the CCR model in the envelopment form in equality. Here theta is unrestricted on side. Note that if we put lambda o equal to 1, because o is one of the NDMUs, lambda o equal to 1 and all the other lambda j equal to 0 and theta equal to 1, s minus and s plus also equal to 0, this solution satisfies to all the constraints, so this is a feasible solution. So lambda o equal to 1, lambda j equal to 0 for j from 1 to n, but not equal to o, and theta equal to 1. This is a feasible solution. This is a feasible solution for the CCR model in envelopment form. And since the objective function is minimizing theta, if we name the optimal value theta star, we name the optimal values of the variables also by a star. So we know that the optimal value in minimizing form is less than or equal to any feasible solution for the objective function. So we have theta star is less than or equal to 1. We can also show that theta star is bigger than 0, since theta cannot be 0 here, since if we put theta equal to 0 here will be 0. So from these summations that all are non-negative, we should have S minus is equal to 0, and summation of lambda j xj, j from 1 to n also should be 0. Since from our assumption of semi-positivity, each xj has at least one positive component, so we should have all the lambda j equal to 0. And by putting the lambda here, and since s plus and y or r non-negative, so we should have y o equal to 0, indeed less than or equal to 0, but we know that y o is semi-positive, means is bigger than or equal to 0 and is not 0. That means at least one of its component is strictly positive. So we have also the optimal objective function value of the model bigger than 0. So theta star is between 0 and 1. Note that by minimizing theta, we find a combination of inputs and outputs which belong to the production possibility set, that this combination is less than or equal to theta star x. When theta star is 1, it means that we cannot have a combination that use a ratio less than 1 of inputs to produce the outputs. But when the theta star is less than 1, it shows we can produce the outputs, at least the outputs of DMUO, with the smallest ratio of the inputs. So it is obvious that when the theta star is less than 1, the DMU is dominated by this combination of inputs and outputs produce at least the same outputs with less inputs. However, if even theta star is equal to 1, as we shown before, the DMU can be also inefficient when the S-lags are not 0 in at least one optimal solution. Indeed, if we have an optimal solution that theta star is equal to 1, but the optimal value of S-lags are not 0, we also have a combination of inputs and outputs of the DMUs that produce the output, at least these outputs, with the same inputs, less than the same inputs of the DMUO when S minus is not 0, and produces more outputs of DMUO when the S plus star is not 0. So to determine if the DMU is efficient or no, we should solve a two-phase model. The first one is this. Indeed, we first solve this model, and then by putting the optimal value of theta, we search for the slags. If there is an optimal solution that have positive slags, so this is the phase 1. But for the second phase, we solve this model. Indeed, we want to search if we have S-like values that are not 0. So we maximize the summation of the S-likes. We name it omega. Here E is a row M vector of ones, and this E is a row S vector of ones. So this is indeed summation of all the components of the slack variables. We have the same constraints, but we only should put the optimal solution of the first phase instead of theta, because we are searching in the optimal solutions. And this model is solved as the second phase. By solving this two-phase LP problem, let's explain here what is E and ES. Note that in the second phase we may replace the one value by other values as the weights, and instead of minimizing the summation of the S-likes, we can use other ways that are positive row vectors, as you can see it from here. By solving this two-phase model, we have this definition: max slack solution, zero slack activity. An optimal solution of the second phase is called the max slack solution. If the max slack solution satisfies the optimal values S minus star equal to 0, and the optimal value of S plus star is equal to 0, then it is called zero slack. And this is the definition of CCR efficiency. Indeed, another definition we had, definition 3.2, CCR efficiency, radial efficiency, technical efficiency. If an optimal solution of the LPs above satisfy theta star equal to 1 and is 0 slack, which means the slack values are equal to 0, then DMU is called CCR efficiency. Otherwise, the DMU is called CCR inefficient because theta star equal to 1, all slacks are 0, must both satisfy if full efficiency is to be attained. The first condition, theta star equal to 1, is named radial efficiency. It is also referred to as technical efficiency because the value of theta star less than 1 means that all inputs can be simultaneously reduced without altering the mix in which they are utilized. Sometimes when the first condition only is satisfied, we use the name of weak efficiency, and when both of these are satisfied, we say the DMU is strong efficient. Conditions 1 and 2 together describe what is also called a strong efficient or Pareto Kopman, that we have it in definition 3.3. Pareto Kopman's efficiency. A DMU is fully efficient if and only if it is not possible to improve any input or output without worsening some other input or outputs.